angle, and you're considering the diagonal OB. So as you walk along there, the temperature is going to vary, and you're going to draw a graph of that temperature variation. So essentially, I mean, X is really along this axis, but as you walk along here, your X is changing, and since you're fixed to a line, you know how Y is changing as well. In fact, at every X value, your Y is a half X, because this is 2 and this is 1. Yeah? So that's information that's useful, and X is varying between 0 and 2, and as you walk along here, Y varies between 0 and 1. Yeah? Q of X is the temperature along this line. So as X varies, Q of X is going to be the temperature, and it's actually going to be the intersection of where's your mouse? If you do that. If you rotate that back to so it's the right way up. Right, so you've got a plane intersecting this graph, and in fact a plane intersecting the two-dimensional graph, that will give you the one-dimensional graph you want. In fact, it's going to start at 0 and end at 0. And it's going to do something like that.
You'll end up with a 2D kind of contour plot thing, will we end up with...
No, you won't end up with a contour plot. You'll end up with a graph of this function Q of X. So you're going to have X along here, Q of X along here. And it's going to rise, and then it's going to go back down again. As if you imagine walking over this hill, your height. You can start at 0, you're going to go up, and you're going to come back down. You can also link it with this, because as you walk along here, at some point you'll go through the centre of the play, and you know what the temperature is there from the previous play. So your graph value at this point should correspond to your value K here. That's just a little check. Because at some point you will go through the centre of the play. So you should record the temperature there, K. So what is Q of X? How do you get Q of X from phi of xy? You've been working with phi of xy all the way through. So what's the link between Q of X and phi of xy?
Is it with only either the x or the y variable, as opposed to, so it would be phi of x as opposed to phi of xy?
Would it be that instead of plotting x against y, you'd have x against Q of x?
No, I'm asking you, well, what I'm asking you now is, you've been working with phi of xy, which is a function of two variables, xy varying over the rectangle. Now you're only interested in this line, which is just, the temperature along here is just a function of x. So how do you get from phi of xy, which is what you've been playing around with, to this thing that you want, Q of x? How do you get from phi of xy to Q of x?
Well, if you go back to the Q of xy, wherever it's got a y variable, the equation changes in place of a half x.
Correct. Exactly.
And then you just do plot 2D, blah, blah, blah.
No, you won't be doing a 2D plot, because Q of x is just an ordinary function of one variable. So it's just an ordinary, like you did with the original f of x or whatever.
It's just plot subs.
So there's various steps. First of all, you've got to construct Q of x, which, as you say, everywhere you see y, instead of phi of xy, it's going to be phi of x, and you're going to replace that y with a half x. So that will be a subs command in Maple. Subs y equals a half x. That'll give you Q of x. In fact, what you'll have is Q of x with an extra big N, as you've always had, because you're going to be able to vary big N according to accuracy. So in fact, what you'll have is Q square brackets N round brackets X equals subs y equals a half x phi square brackets N xy. Which will give you Q of x, but with this extra n, as usual. And then you're going to plot that, and you're going to have to subs for a value of n, and change that value of n to get better plots.
Okay. And would 50 be enough for...
Well, you're going to play around, start. Whatever value of n you've used before, I would use that value of n to plot the...
Okay.
You want to be consistent.